Talk is by Adam Marcus from Princeton, and he'll tell us about existence proofs of Ramanujan graphs.
Thank you very much. It's maybe unfortunate that this talk wasn't before Will's, because it's going to fill in maybe some of the gaps that he wasn't able to cover. But I'll try very hard to point out places in my talk where the things that he said are relevant. So this is two existence proofs of Ramanujan graphs, and it's joint work with Dan Spielman, who's at Yale, and Nick Hill, who is here at UC Berkeley. All right, so I want to start with our motivation, which is sort of a problem in combinatorial linear algebra. That's what we call it. And the question is this. So if I have A1 through AN, which are independent, random, positive, semi-definite matrices, I want to find upper bounds on the lambda max of the sum over I. This should be, sorry, no hat here. The sum over the AI, where the AI are in the support of the AI, of the AIs with the hats. So I have these random matrices that I'm concerned about. What I want to do is cheat, and I want to find the assignments which give me the smallest maximum eigenvalue that I can possibly get. And I want to figure that out. I want to get bounds on that thing. And one way we could try to do it is using the probabilistic method, right? If we can show that the probability that this lambda max of this thing is less than t is greater than 0, then what we would be able to show is that theta is less than t. Right? There would be something that satisfies that. And there are numerous techniques for bounding these types of quantities, this probability of lambda max of these sums of matrices. And there's a whole sort of series of these. They're called matrix Chernoff, Bernstein, Hufting, all of these, Azuma, which say that if A1 through AN are in Rd by D, are independent, random, positive, semi-definite matrices, then you get a bound exactly what you need. The probability that lambda max is greater than t is less than or equal to d times some e to some function that's grows very fast. So this thing gets very small, but at the same time, there's this d here. So there are similar inequalities by Rudelson, Alswede-Winter, and Trop. And all of them have two things in common. They're concentration bounds, and the bounds depend on the dimension, right? This d here. And it sort of has to be that way. So this is the bad seed. So if you picked V1 through Vd to be independent random matrices, which just took each of these matrices uniformly at random, so with probability 1 over d, then it should be clear that theta V1 through Vd equals 1, right? Because for each Vi, I pick a different one of these matrices. It adds up to the identity, so that's the highest you can get. But as a probability problem, this becomes a balls and bins problem, right? You're throwing diagonal entries, and you're asking when are they all in sort of separate bins. So assume you have n identical balls. For each ball, you pick one of n different bins. Then if Zi is the number of balls in bin I, then the well-known fact is that the expected maximum Zi is log n over log n, so something that grows to infinity, certainly not 1. Even worse for us, the probability that you are close to this thing is very close to 1. So there's not really anything that's going to be able to drag us down. And if we were trying to get something that was asymptotically tight for this problem, we're in much bigger problems, because the probability that you actually get 1 is something that's exponentially small. OK, so what this example shows you is that if I wanted to get better bounds, let's say asymptotically tight bounds that don't depend on the dimension, then I'm going to need to start find a way to capture low probability events. And this was previously not possible in a spectral setting. The sort of thing that the Lovász local lemma does. And the key idea for us was to switch from matrices to polynomials. So the characteristic polynomial of a matrix is the determinant of x times the identity minus that matrix. And the key fact is that the roots of the characteristic polynomials are the eigenvalues of A. So for any self-adjoint matrix, we can replace this lambda max of A with maximum root of the characteristic polynomial of A. And for a random matrix, we can say the probability that lambda max of A is less than or equal to t is the probability that's the max root of chi A of x is less than or equal to t. This is just looking at exactly what we have. And this suggests studying random characteristic polynomials. And my first claim is that this is kind of a silly suggestion. But I have a section on it, so it can't be that silly. But let's see what actually I'm saying. So if A is a matrix, and V is a random vector taking values U or W uniformly, then what would we be considering? We'd be considering 1/2 times the characteristic polynomial where we've added UU transpose, plus 1/2 times the characteristic polynomial where we've added WW transpose. And there's this issue that when we add polynomials, it's a function of the coefficients, right? And we're interested in the roots. And going from roots to coefficients is easy. You just multiply out the polynomial, x minus the roots. But going from coefficients to roots is hard, right? This is what Galois theory tells us. And in particular, you may not even have a sum that makes any sense with respect to your original thing. So here are two polynomials p and q. One has a double root at 1, one has a double root at -1. And when you add them together, you get roots that are imaginary numbers. And so it's hard to be able to compare 1 and -1 with square root of -3, for example. But it turns out that a special condition sort of allows us to be able to do that. And we call it root separation. So if the pi is a collection of degree d polynomials, and st is an interval such that all of the pi of s are greater than or equal to 0, and all of the pi are less than or equal to 0 at t, and each pi has exactly one real root in st, then the sum over I of pi has at least one real root in st that lies between the roots of some pa and pb. And the proof is very easy. And I'll show it by picture. So if everyone is positive at s, then that means their sum is positive at s. And if everyone is non-positive at t, then the sum is non-positive. So at some point, the sum crossed 0. So it has to have a root there. And if you look at the point where the root crosses 0, this is going to be a sum of values of polynomials which add up to 0. So one of them will be greater than or equal to 0, and one of them will be less than or equal to 0, and that one will have a root which is on either side of this root. So, and the point is that if you happen to have d such intervals, what does that mean? That means you have d intervals with at least one real root in it. Well, when you add these two degree d polynomials together, it's a degree d polynomial, so it only has d real roots. So it must be that it has exactly d real roots, and there's exactly one root in each of those places. And if you sort of iterate this argument, you get a bound, which, at least in the rank 1 case, which was mentioned by Will in the previous talk. So if A1 through AN are random independent rank 1 positive semi-definite matrices, then if I let p of x be the expected characteristic polynomial, so for each matrix I form a characteristic polynomial and average those characteristic polynomials, that happens to have only real roots, and there exists an AI and an AI prime in the support of these AIs, such that the kth root of when I plug in all the AIs is less than the kth root of this expected one. And the kth root of when I plug in the AI primes is greater than or equal to this one. So this expected characteristic polynomial is somehow a bellwether for both directions.
They have the same distribution.
Excuse me?
AI comes from a distribution, right? They all have the same distribution.
No, they all have different distributions, and they're not really okay. So, and they're not really, classical random matrices necessarily. You could pick I have matrix A, which I really like, and matrix B, which I kind of like, and I choose between the two of them. right? It's not necessarily like random as in the entries are random or something like that. It's just essentially.
I can think, I mean, a delta function would be the worst case, right? It's not going to be. I mean, there should be a condition on the distribution, right?
No, so there's no condition on it. I mean, apart from being independent. Yeah, I mean, if each one was only one, then this would be a silly statement, right? There would be equalities everywhere.
What does it mean, the support of AI?
I mean, the collection of AIs that AI hat is allowed to be. Right, so if I pick between A and B, I want to be able to plug in either A or B and be able to get something. And the claim is that there's an assignment of the first AIs that happen with maybe not non-zero probability if you have a continuous distribution, but in a discrete setting, a non-zero probability of having those AIs and a non-zero probability of having these AI primes, such that they sort of surround the root of the.
Is the quantification over K, is it for every K there exists, or?
For every K, there exists such an AI, a collection of AIs and AI primes. Yes. Yes. That will actually come in later. Important. And I should mention that Michael Cohen, who's a grad student at MIT, has a way to extend this to larger rank matrices, but only if you're interested in the largest root. So his theorem says that if A1 through AN are random, independent, positive semi-definite matrices of any type, then the bound that you're supposed to look for is the one that you would get if these BIs had been rank 1 matrices, random rank 1 matrices, in such a way that the expectations match up. So he calls this rank 1ification. And both of these proofs use what we call the method of interlacing polynomials, but that's not really what I want to talk about today. So I want to switch gears to talk about expander graphs. And Will mentioned earlier that sort of the ultimate expander graph is the d-regular infinite tree, right? And so in some ways, when we're talking about what makes a good expander, we should be asking what makes a good approximation of this tree as a finite graph. And of course, in spectral theory, our definition of good is going to be in terms of eigenvalues. And it turns out that the spectrum of the d-regular infinite tree lies inside this interval minus 2 squareds of d minus 1, 2 squareds of d minus 1. So the question is, can we get a finite graph to have all of its values inside this interval? And of course, the answer is no, particularly because the adjacency matrix of a d-regular graph has at least one what are called trivial eigenvalues, which corresponds to the all-ones vector, which has the eigenvalue of d. And if your graph happens to be bipartite, then minus d is also an eigenvalue. And so we call those eigenvalues trivial. And then we can ask whether all the rest of them are in this minus 2 squareds of d minus 1, 2 squareds of d minus 1. And if they are, then we call it a Ramanujan graph. And if we have a collection of these things that are all d-regular, we call it a Ramanujan family. And the famous theorem of Alon and Bopanna says that you can't do any better than this. So if you have any smaller interval, you cannot possibly contain all of the non-trivial eigenvalues of an infinite collection of d-regular graphs. So this is the best you can hope for. The question is, can you do it? And the answer was confirmed in the positive by Margulis and separately Lubatsky, Phillips, and Sarnak, who proved that Ramanujan families exist when the degree of the graph is p plus 1 for p a prime number. And this was extended by Morgenstern to d equals p to the k plus 1, but was unknown for all other d. And their constructions were algebraic, right? They were Cayley graphs of some very highly structured groups that they were able to reason about. Then again, on the other hand, almost everything is almost Ramanujan. So a theorem of Friedman says that if you're willing to be off by some epsilon, then as n gets large, you will be within that epsilon with extremely high probability. So the obvious question is, are Ramanujan families really a special artifact of these algebraic structures, or do they exist in some other generality? And I'd like to give two proofs of their existence. So the first proof, which is what Will's proof was an extension of, I'm going to call the topological proof. And the idea is, like he said, using covering spaces. So it's easy to find small graphs that are Ramanujan. So for instance, KD, the complete graph on D vertices, has all non-trivial eigenvalues -1. And KDD has all non-trivial eigenvalues 0. So that's easy to be Ramanujan. And Bilu and Lineal suggested treating the average D-regular graph as a quotient of the infinite degree D tree with respect to a covering map. So what was their idea? You start with KD or KDD, and you construct a sequence of graphs that interpolates between KD and your original graph and your infinite tree, D-regular tree, using a series of what they call lifts. And what does that mean in a graph setting? So in a graph setting, you would start with a presumably Ramanujan graph, and then you would make a copy of it, possibly many copies, and then you would do some perturbation to these edges. And the goal would be to then try to find some perturbation that makes this new graph Ramanujan. Supposedly, since you started with the Ramanujan graph, that maybe is not as hard as just picking edges randomly. So Bilu and Lineal suggested perturbations they called two-lifts. And a two-lift comes in one of two versions. Either there's a positive edge lift or a negative edge lift. And the action of each two-lift can be described by a signed adjacency matrix. So, which is exactly what you would think it is. It's the normal adjacency matrix, except rather than all ones, you put a 1 if there's a positive edge and a -1 if there's a negative edge. And this is the matrix that you would, in Will's construction, you would replace rather the ones with ones and -1s, ones with blocks of permutations, and then the respective other conjugate permutation, or inverse permutation. And what Bilu and Lineal showed was that if G is a D-regular Ramanujan graph with n vertices, and you have S, which is assigning of the edges, so you put plus or -1 on each of these things to determine whether you do a positive or a negative swap. If all of the eigenvalues of AS lie in this interval, -2 squared of D -1, 2 squared of D -1, then the two-lift is also a D-regular Ramanujan graph, but now it has two n vertices. Right? So this is essentially what Will said, that the eigenvalues of this new graph are going to be a union of the eigenvalues of the old graph with the eigenvalues of some modified adjacency matrix. In our case, it's a signed adjacency matrix. In his case, it was his block adjacency matrix. And if you start with something that had good Ramanujan, that had good eigenvalues to begin with, and this new thing has good eigenvalues, then the whole thing has good eigenvalues. And they conjectured that every D-regular graph contains such a signing. And we can prove this conjecture for every bipartite graph G. And I want to mention something about being bipartite. Why is this necessary? In this case, the signed adjacency matrix, you can write it in block form. So you have 0 and then B transpose in 0. And this causes the eigenvalues and eigenvectors to come in pairs. So in particular, if you know that lambda I is an eigenvalue, then minus lambda I is an eigenvalue. And so the corollary is that a bipartite signed adjacency matrix has all of its eigenvalues in this interval, if and only if its eigenvalues are at most 2 squares of D -1. And this gets back to what you were asking about the quantifier. We can only say something about one root at a time. And so in order to bound something in this interval, we sort of have to cheat in a way that allows us to reduce it to saying something about one eigenvalue. And the main idea is to consider the characteristic polynomial of the signed adjacency matrix. And this corresponds to either picking delta I plus delta j or delta I minus delta j, right? You'll get something you'll get d on the diagonal regardless of what you pick. And then if you pick delta I plus delta j, you'll get a plus on the off diagonal, and you'll get a minus on the off diagonal if it's delta I minus delta j. And if you do that independently, then you've satisfied the conditions of our theorem. And so the corollary is that there exists assigning S star such that the maximum root of PS star is less than or equal to the maximum root of the expected polynomial over all signings. So now it suffices to bound this expected characteristic polynomial. And fortunately for us, this has already been done. First of all, what is the expected characteristic polynomial has already been done. It turns out that if you take the expectation over all of the possible signings, you get the matching polynomial of G. This was something that Will also mentioned in his extensions. And separately, in a paper of Heilman and Lieb, which is actually where the matching polynomial was originally introduced in statistical physics, they showed that if G is a graph with maximum degree delta, then the maximum root of mu G, this matching polynomial, is less than or equal to 2 squares of delta minus 1. So this is exactly what we're looking for. So piecing things together, there exists bipartite Ramanujan families of degree D for any D. You start with KDD or KD. You pick a lift. Our theorem implies that there exists some lift whose maximum root is at most 2 squares of D minus 1. This combines the matching polynomial and the bound on the matching polynomial. And then you iterate. And it's exactly what Will was talking about. This technique extends to K-lifts by Hall, Puder, and Sapin. So now I wanted to talk about a quite different proof. It seemed like a very similar proof, but now we believe it's sort of quite different, at least I do, which I call an algebraic proof. And the proof idea sort of comes like this. So if I wanted to understand the infinite tree, one way to do that is to realize that it's the Cayley graph of the free group, right? And in algebra, they have this construction that they call a free product, which allows you to take free groups and build bigger free groups, right? So I can take a free group of size 10, and then I can turn it into a free group of size 11 by adding another copy. And if you've done any sort of computational things with d-regular random graphs, you realize that that's sort of how we also build these d-regular random graphs, at least multi-graphs, is you take a matching and you put it down, and then you add another matching, and then you add another random matching, and then you add another random matching. So they both have this sort of building from pieces sort of idea. And so the question is, can we figure out whether a graph is Ramanujan, or can we build a Ramanujan graph using this sort of construction? This put down a matching, then put down another matching, maintaining Ramanujan-ness, then put down another matching, which maintains Ramanujan-ness, but now for a different D, it'll be D plus 1, but continuing in that manner. And what's happening here? Well, the adjacency matrix of a perfect matching on 2 n vertices has eigenvalues 1 and minus 1 each n times. And when you union these graphs, multigraphs, what you're doing is you're summing the adjacency matrices. So the question is, can I find some permutation of this original matrix B such that the eigenvalues of A plus B are small? Now the issue is that the eigenvalues of A and B, A plus B, depend on the eigenvalues of A, the eigenvalues of B, and then the dot product of the corresponding eigenvectors, right? So the heuristic here, since you have 1s and minus 1s, you kind of hope they'll sort of balance each other out if you sort of distribute everything evenly. So what you want to try to do is to keep eigenvalues low. You want sort of all of these dot products to be as close to uniform as possible. Of course, you don't have very many choices for B because this is a graph polynomial, and A is a graph polynomial, a graph matrix, adjacency matrix as well. So what if we try to add A and B randomly? It's just a thought experiment. So let's look at A plus RBR transpose, where R is a hard distributed random orthogonal matrix. So I'm looking at all possible rotations. Well, it turns out as D goes to infinity, that the probability of having a large dot product with a fixed vector goes to 0. You're sort of almost guaranteed to be far away from any fixed vector. This is a property of volumes in large dimensions. And if you look at this in some sort of limit, this idea of close to uniform happens with probability 1, and the resulting eigenvalue distribution can be calculated. And this has been done, and it's known as the free convolution. And it turns out that, so the study of these types of operations is known as free probability, and it is a very common exercise to compute the convolution of d copies of a Bernoulli random variable, which, if you remember, this is exactly what our adjacency matrix is. And the free convolution of d copies of a Bernoulli random variable is known as the Kessin-McKay law, and it's given here, but for our purposes, the interesting part is that its support is on the interval plus minus 2 square roots of d minus 1, back where we were before. So now you might ask, can we do something similar in finite dimensions, right? We're not really able to push d to infinity, first of all. And the answer is yes. So we call this sort of a quadrature result. So if A and B are n by n matrices, where you know the where p of x is determinant of xi minus a and determinant of x minus b, then we say the finite free convolution of p and q is this integral over all determinants of xi minus a minus r b r transpose over all rotations r. And the finite free convolution of real rooted polynomials always has real roots, it turns out.
Independent of A
I'm sorry.
and B. It's independent of A and B, the choice of A and B.
It depends on the eigenvalues of A and the eigenvalues of B. Yeah.
Only.
Only, yes. So this is a function of p of x and q of x. A harder question, can we do something similar with adjacency matrices, right? We're not allowed to sort of integrate over all possible rotations. Sorry, this is what we call the quadrature result. This is a quadrature for Laplacian matrices. What we can show is that if A and B are matrices such that the all ones vector is an eigenvalue of both A and B, then what you can do is you can strip off this eigenvalue, and you can do the same sort of calculation in the previous thing where you form a convolution, and what you get is exactly what you would get if you took the expectation over all permutations of B of this characteristic polynomial of their sum. Where P is a uniformly distributed permutation matrix. And now, since this is an expected characteristic polynomial, we can say something using this corollary of interlacing families that one of these matrices has to do better than what the average does. So the theory of quadrature for Laplacian matrices extended says that not only does this finite convolution exist, but also there exists a p0 such that the largest root of the, I'm sorry, there should be no expectation here, the characteristic polynomial where you plug in p0 is smaller than the largest root of this expected one.
The P0 now is a permutation or orthogonal matrix?
P0 now is a permutation.
How do you know that you have?
Because we can do this as a sum over permutations. Right? What we showed is that that summing over permutations, at least in the case which is orthogonal to the all ones vector, gives you the same answer as what you would get if you did the rotation. So you can do the computation using all the rotations, but then you can get a guarantee that one of the permutation matrices does it.
So is it conceivable that that could also deal with the non-bipartite things? With the general signing conjecture?
Yes, it's certainly conceivable, yeah.
So, I mean, can you state a conjecture that would lead to the solution of the signing conjecture in this context?
So I'll mention something at the end, maybe. And our original proof uses random swaps to build an interlacing family. I think probably we don't even need that now with Michael Cohen's result that allows us to use general matrices. So lastly, we need to compare, we created this finite version of a free convolution. We need to compare the free and finite free convolutions. And what we're able to show is that the support of the finite free convolution of two distributions always lies inside the support of the free convolution of those distributions. So the largest root is always smaller than the edge of the spectrum of the free convolution, and the smallest root is always larger than the edge of the spectrum of the left edge of the spectrum of the free convolution.
Finite free is average over symmetric group.
Finite free is an average. The finite free is this computation
Average over symmetric.
here with just finite matrices.
But Sn
Regular
all
over all of the
all this.
orthogonal group, of the entire orthogonal group. It turns out not to matter. So you can do orthogonal group, you can do the unitary group, you can do the so because these are essentially the first order Jack polynomials, so like they're all the same on, and they're independent of beta. And then you can do that. So then when d goes to infinity, that becomes the real free convolution. And what we can show is that the finite version is inside the spectrum of the free one, of the infinite one. So putting everything together, this gives that for all d and all even n, there exists a d-regular bipartite Ramanujan multigraph on n vertices. So very similar to what Will was able to show. And I should disclose that because of the bipartiteness, the actual proof of this is a little more complicated. Like we need to use a different convolution which preserves bipartiteness. But the proof idea is sort of similar. It just uses singular values rather than eigenvalues. Okay, so the first question I want to talk about is this idea of a polynomial time construction. So certainly has already come up. And a theorem of Michael Cohen again, the grad student at MIT, says that the Ramanujan multigraphs which were provided by the second proof are constructible in polynomial time. And the way he does this is he sort of takes these polynomials and extends them to what are called real stable polynomials by adding extra variables, and then he uses those variables to sort of keep information which sort of gives him hints about what the original, which of the two, whether the plus or the minus was chosen for each thing. And I should remark that matching polynomials in particular are probably not constructible in polynomial time. Just in particular, the zeroth coefficient is the constant coefficient is the number of perfect matchings. So certainly the first way, any sort of naive way of trying to implement what we're doing here is probably not going to work, because you would have to, in particular, construct a matching polynomial. It's certainly possible that there's some sort of like random walk way of doing this that, you know, could find some minimum and doesn't actually know what the minimum is, and then this could show that this is the minimum, but at least the naive way of doing it certainly wouldn't exist. On the other hand, there's the similarity is that they both use this method of interlacing polynomials. And in particular, the two things I want to point out are that in the first case, well, in both cases, the expected characteristic polynomial was computable. There's absolutely no reason to believe that when I integrate over a bunch of like random polynomials that I should be able to figure out what that polynomial is. And secondly, the bounds were asymptotically tight, right? It's, you know, as we saw with Friedman, it's very, well, I don't want to say easy, but it's certainly not algorithmically hard to find something that's very close to Ramanujan. But it turns out to be a little bit more complicated to get on the other side of Ramanujan. And if you remember what the bound I gave you at the very beginning with these polynomials, I mean, when I gave you this bound, it sort of is like me telling you that I'm taller than my cousin, right? I mean, so on one hand, if you don't know who my cousin is, that means nothing to you. And secondly, if you know that my cousin is 2 years old, that also means nothing to you, right? I mean, so you have to be able to construct this, and it has to actually be good. So it's sort of nice, and a similar, one similarity is that both of these happen in this case. The difference is, one is that the output of the original one is is guaranteed to be a graph. In the second one, we have no way of ruling out the possibility that you could get a multigraph, which is a Ramanujan multigraph. And of course, the first one we believe has no construction, and the second, or at least any naive construction, and the second one does contain a construction. And recent work tries to explain why these, what the differences are between these two methods, and it comes down to a theory that we call finite free probability, which is essentially understanding these operations of finite free convolution in the same way that free probabilists understand their free convolutions. So future work, here are some questions that I'm particularly interested in. So the first question is to complete the analogy. So we've seen that you can sort of do this finite free probability by doing a combination of univariate polynomials. We have very similar things. So it's actually been very nice that many of our results are related to the results in free probability. Because every time that we have a question, we can sort of look and see what the similar answer is in free probability, and that gives us sort of an inspiration as to what to look for. In the multivariate case, we have no idea what this correspondence is, whether it exists or whether it's, you know, some extension of free probability that we don't know. But if somebody had any ideas on that, I would love to know. And in particular, you can think of this comparison of finite free convolution with free convolution as a statement about operations that combine polynomials into a new polynomial, what the bound on the roots of this new polynomial are based on the roots of the original two polynomials. One interesting question would be whether there's a similar inequality in the multivariate version that in particular would imply this Heilmann-Lieb bound. So if you look at the original proof of the Heilmann-Lieb bound, it very, very intimately uses the fact that it is a matching polynomial and not just a polynomial that's going under, that's being, you know, just having something done to it. And if you move to the multivariate case, you can sort of turn at least the proof that this thing is real rooted into sort of a property of polynomials rather than a property of matching polynomials. And so, so then another question is root inequalities. One thing we've noticed is that in a lot of situations there seems to be this majorization order that goes along with various operations. And if you could find something like this would imply exactly what you're asking, that the largest and the smallest root are both smaller. And in particular, doing such a thing would get rid of the word bipartite. I want to sort of advertise other applications of this finite free probability idea. So apart from the additive convolution, we have a multiplicative convolution. We have additive and multiplicative Brownian motions. We have some idea of what entropy should be, Fisher information, and recently a combinatorial theory has been built around it. So sort of a correspondence between, in the classical case, the moment cumulant formulas has a corresponding moment cumulant formula in the free probability case, and they were able to develop the corresponding one for this finite free case. And there's already been certain, sorry, did somebody have a question? Okay. There have already been some noticeable applications. One is to what are called discrete Gaussian free fields. This is a result of Vadim Gorin, and also to what is called Weingarten calculus, and this is an observation of Jonathan Novak at UCSD. But combinatorially, we don't have any other sort of applications of any of these types of things. So thank you for letting me speak today, and thanks for your attention.
So just trying to understand something. The second proof implies that if you start from any Ramanujan graph, you can always add the matching and keep it Ramanujan?
Yes.
And is it true, so you can also always add, if you have two Ramanujan graphs, can I put one on top of the other? and keeps them wrong.
That's more complicated.
Should it be true?
It should be true. You'd have to do the free probability calculation, right? I mean, there's something special about the 2 squareds of d minus 1 that comes out of this Keston-McKay law, and that's the fact that when you
Simplest to add a Hamilton cycle than to keep it from Ramanujan. 2 matchings is a cycle, but maybe it's a union of.
So actually, I might have to go back on what I originally said. So it may be. So I'm not positive that if you started with any Ramanujan graph that you could add something that's Ramanujan, because somehow it would depend on the distribution of the original graph. But
It doesn't follow from your
Yeah,
proof.
how does
I mean,
the-
in your
how-
proof
how-
you only assume
Yeah,
no, I take it back. Yeah, I think you're right. Yes,
take it forward.
I retake it.
Another thing, so you said that this proof is algorithmic, or this result of Cohen?
Yes.
So he can find the permutation?
He can find you permutations. If you wanted to pick a D and an N, he could build you a Ramanujan graph of degree D on N vertices that might be a multigraph.
Right, yeah, it's more interesting.
Bipartite.
So he can find the permutation by,
Yes.
by some, okay. And you said something about how this goes.
Yeah. He sort of he keeps around. He turns these one univariate polynomials into multivariate polynomials, and the way he does it sort of keeps more information about what's happening. So he's able to look back at what the coefficients of these new variables are, and use that to determine which of the permutations was the one that did it.
Other questions? All right. Thank you.